Hey there. Today we're looking at 2.5, graphing special functions. And so we're going to look at three types of functions in this section. And you're going to see that in our objectives today. And so our three types of functions that we're going to look at are piecewise, step, and absolute value. Now we looked at absolute value a little bit in 2.6. And again, with me flopping these sections, that's why we saw it in that section. But we're going to look more in depth at that along with step functions and piecewise functions today. And so that falls under these three standards of ACE2, again, creating equations in two or more variables, being able to graph them, interpret the key features, including sketching with intercepts, increasing, decreasing, and so on, and then being able to graph from symbolic representations, including their intervals and increasing, decreasing. So again, that's the standards that we are looking at there. And so our first type of function we're looking at is a piecewise defined function, or we'll just call it a piecewise function many times. And this is a function that is written using two or more expressions. And so we're going to look at a very simple case to start. And so in example A, we've got f of x is equal to x minus 1 if x is less than or equal to 3. And then f of x is going to be 1 if x is greater than 3. So what this is, these are our domain values. And it's telling us where we're going to have this function. Our function's not going to be, at least for this piece, the entire graph. It's only going to be where x is less than or equal to 3. And so as we look at our function, now if I just graphed x minus 1 across this graph, my y-intercept's negative 1, and my slope is 1 because there's a 1 in front of the x. And so my line would just slope up like this going on forever. But my problem is it stops at 3. And so we have to think about having like an imaginary line right here at 3. Now I'm using a dashed line just to show that line's not real. It's just guiding me as I draw this picture. And so as we stop here at our green line, now my line is going to go less than. So it's going to be all of this going this way, going on and on forever, right? But it's going to stop at this green line. Now go back to inequalities. If I'm equal to, what do I put at the end? I put a dot. If I'm not equal to, like our second piece, what do we put? We put a circle. And so our second piece looks like this. I'm going to change colors here. It's negative 1 when x is greater than 3. So x being greater than 3 would be to the right of this green line. Now, I've just got the value negative 1, which means it's a constant function, which means it's a horizontal line. And so it's going to be at negative 1 going out like this forever when x is greater than 3. But remember what we said. If it's just greater than or just less than without the equal to part, we got to put a what there? Got to put a circle, because that means it is not equal to at that value. And so what we end up is these two pieces. Now, let's talk about domain and range, because that's the second part of this graph. And so the domain, remember, domain would be what x values is this graph defined for? Well, it goes from x being less than or equal to 3 and x greater than 3. So I've got an x value everywhere along this graph. So my domain is all real numbers, or negative infinity to positive infinity. My range is a little bit more interesting because remember, it's what y values I could have, or I do have, based on the graph. And so when we look at this function, this blue piece is going to go down forever. So I'm going to go to negative infinity. But where do I go to top out? Well, the highest point I have is right here at this ordered pair of 3, 2. And so the highest y value I have for the entire graph is 2. And so if you're writing this in inequality notation, we'd have that y would be less than or equal to 2. Had I had a circle here, let me make a correction here. This should be a bracket, not a parenthesis, because I am equal to, not equal to. Because again, if I'm equal to, we'll have a bracket. If I'm not equal to, it'll be a parenthesis, and of course that symbol would change. So again, domain is what x values do I have for the function. Range is what y values I have for the function. So as we look at example B, we're going to reverse our directions here. We're given this graph, and we want to write the piecewise function, identify the domain and range. And so let's first identify the two pieces. So our first piece, I'm going to draw some lines to help us out here. So again, we see that both these functions stop on this green line here. And so it's best to first identify how many pieces we have. We have 2 pieces. So piece 1, piece 2, right? For our f of x being equal to it. So piece 1 is going to be this piece over here. And so when we write out these directions, we're going to put the word if, and then we're going to put our domain. And so for the first piece, x is less than or equal to -1. Because we're talking about this piece over here. This line is at x equals -1. And we've got a dot there. Now, what value is that? -1, -2, -3. This is at -3 if x is less than or equal to -1. Again, because this is just a horizontal line that is extending to the left. Our second piece is from here, and it's x being greater than, because I'm to the right of this green line, and it's not going to be equal to because we're a circle, not a dot. And so I've got to figure out this -1 here. I've got to figure out the slope and y-intercept. Well, the slope goes from here to here, so that's up to right 1. So I've got a positive 2x, and my y-intercept is at 1. And so I get 2x plus 1. So again, I identify the 2 pieces because of their slopes and y-intercepts, or their potential slopes and y-intercepts. So let's say this line didn't cross the y-axis. I could continue the line through to see where would the y-intercept be, or I could put it into like point slope form and then convert it to slope intercept form. Now the second part of this question does ask us what is the domain of range. And so the domain, there's no x values that we don't have some value for. So our domain again is all real numbers. That will not always be the case. We could have gaps in our functions. And we're going to see that with our range here. Our range is not all y values. There's 2 different pieces. Because for this piece, our range starts at -1, right? It's not included at -1 because there's a circle there, and goes on to positive infinity. So if I was just talking about this piece, the range is from -1 to infinity. We're talking about the range here. We're talking about this piece, the range is just the y value that it's at, and so the range of this piece would just be -3. And so when we look at our values here, we're going to do 2 things. We're going to first define it this way, and we're always going to work from least to greatest. And so I've got -3, and that's going to be in brackets because it's the only value of that part. And then I've got the other piece, which is -1 to infinity. Now, we're used to putting the word or here, right? If we're talking about 2 separate pieces, it'd be this piece or this piece. But in interval notation, we're going to use this letter U, which means union. And that means that we have at -3, it's inclusive just of that point, and then from -1 to infinity, not including either endpoint. If we want to write it out to self-builder notation, it would be y such that y equals 3 or y is greater than -1. Again, it's not a pretty write out, but it is what it is. Okay. So we're going to continue with piecewise functions. Now we see one where we have 3 pieces that we have to graph, and we have to pay attention to what goes where. And so again, I'm going to use some green lines here to separate out my domains. My first domain is where x is less than -2. So I'm going to put a green line at x being -2. My middle piece goes from -2 to +3. So I've already got a line at -2, and so I'm going to go to +3. And my third piece is when x is greater than 3. So I've already got a line at 3. And so we're going to look at our 3 pieces here. And we'll do one at a time. So I'm going to start with blue for this first piece up here. F of x is -3 if it is x is less than or equal to -2. And so that, remember, if I'm just a constant value, I'm a horizontal line. And so at -3, I'm going to have this horizontal line out this way. Do I have a dot or a circle at -2? It's a dot because I'm equal to. So I'm going to put a dot here and connect my little piece. My middle piece is the next part, right? And so it's 2x minus 5 in this middle section between -2 and +3. So my y-intercept's -5. So I'm down here, y-intercept -5. and my slope is 2. So I'm going to go up 2, right 1, up 2, right 1, up 2, and right 1. Now we'll talk about this point here in a second, what we're going to have. And I can continue my line down 2, left 1, down 2, left 1, and again we'll talk about what happens there. Well, look at my inequality. Let me erase the green so we can see what's actually there. It's not equal to and not equal to on both ends. So if it's not equal to on both ends, I'm going to put circles on both ends. Had one end been equal to and the other end not been equal to, we put the appropriate dots and circles where they belong. And so these two pieces are going to connect, make our line, our segment through there. Now let's talk about our last piece, negative x plus 5 when x is greater than or equal to 3. And so our third piece, let's go with red here. So this piece is in red. The y-intercept would be 5 if I hit the y-intercept. So I'm just going to put a very small little red dot there, because that's not actually going to be in my domain. My domain is when x is greater than or equal to 3. It's over in this region over here that this line's going to be. My slope is negative 1, so I'm going to go down 1, right 1, down 1, right 1, down 1, right 1. And now I finally end up in the region that I'm allowed to be in. So these first dots that were up here will get erased because they're not actually part of my piecewise function. They're just guide points to get me to the right spot. Now, another way we could just get this first point here, we could plug in our x value of 3, and then we get negative 3 plus 5 is 2, and so we end up at a y value 2. And it is a dot there because I'm equal to, and so this piece is going to come down like so. And so again, we've got a dot there. Now, these two pieces don't technically overlap. If these two pieces had lined up, then the dot takes over for the circle, because then we would have a value there. But because they're not at the same point, we will have the circle at 1 and the dot at the y value of 2. Okay, and so this one didn't ask for domain and range, but if we were asked for domain and range, the domain again is all real numbers because there is nothing in this domain that is missing. We've got an x value the entire way across. My range becomes the more interesting piece. What values do we get? Well, this piece just gets me negative 3, okay? And that's covered by the orange, so I'm going to ignore the blue. The orange is this segment here. And then we get the red, which is up here and going all the way down and continues down forever. So the only piece I really care about in this one is the last one. And its range would be y being less than or equal to 2. And so in set notation, that would be from negative infinity to positive 2, or y is less than 2, less than or equal to 2. So now we look the other way. We've got 3 piecewise functions here. And so let's identify each piece. And so identifying first the red piece, okay? So the red piece, so f of x equals, the red piece, we've got a slope going up 2, right 1, so my slope is 2x. And if I continue this up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, I end up with a y-intercept of 10. Now remember, I could do this a different way. We could talk about taking this to point slope form, and so, you know, y minus y sub 1 equals m times x minus x sub 1, and I could do y minus, this point is at negative 4, 2, so there's my 2. We said my slope was 2, x minus the negative 4, y minus 2 is equal to 2x plus 8, double negative becomes positive, times by 2 is 8, and then add the 2, and we get y equals 2x plus 10, which is what we had up there. Okay, so the first piece checks out. Now we got to talk about where's this at. So if, right, and we're going to have 3 ifs because there's 3 pieces. This first piece, draw our nice little green here down where this is at. We're at x less than negative 4. The middle piece, the piece in green, we see we've got it from here to here, and so we're going from the negative 4 to positive 2. So negative 4 less than or equal to, because it's a dot, x less than or equal to, because it's a dot on this end, 2. And so what's our function? Well, we have our y-intercept, so it's going to be a plus 5. And what's our slope? We go down 1, right 4. So I'm going to have negative 1/4 x plus the 5. For our blue piece, our last piece here, we see it's a circle here, so we're going to be x greater than 2, and then we're at one constant value, so it's just 1. So as we identify these pieces, take one piece at a time, figure out what it is. Okay? Again, use your skills of knowing how to find lines, how to graph lines to get each individual piece. Okay? And I would also say the other key thing, make sure you know where are your breaks. And you could have more than just 2 breaks. You could have pieces where the dot and the circle don't overlap. You could have a gap in between where they're at in terms of x values. And so that would change our domain to be disjointed as well. All right, so let's talk about step functions. Step functions is a graph where it's a series of line segments. And there's 2 types of step functions that we really talk about. One is the greatest integer function, and the other is the lesser or the least integer function. We're going to focus on the greater integer function today. And that means we're looking for where the greatest integer is less than or equal to our x values. And so we're going to look at this step function here. It says that one psychologist charges for counseling sessions at a rate of $85 per hour or any fraction thereof. Now, if we were doing just a normal linear problem, it would not include this wording here. It would just be that it's $85 per hour. And we would just draw a line where, after 1 hour it's $85 and 2 hours would be $170 because, if you went for an hour and a half, you'd pay for an hour and a half. You would do 85 times 1.5 and get your value. But that's not what happens here. What happens here is that if I go for 5 minutes, I'm going to pay the full $85 because it says any fraction of the hour I pay for the full hour. And so as we look at our function down here, we're going to get f of x is equal to, and this is the notation you'll see in the book. It's this little double barred bracket, kind of like our sets of like real numbers and whole numbers and such. And our function will go in here. Now, again, we could have parts outside, as we talked about with transformations yesterday. We could have parts out back where this is translated up or down, and we're going to see that in this case. And so we're told that it is $85 per hour. Now, the hours is what we're rounding up. So h will go in here, or in this case, we'll use x since that's what we used for the variable out here. But we're multiplying our hours by 85. And so what we get in our picture is this. Again, we said if I go for even 5 minutes, I'm going to pay the full $85 all the way up to 1 full hour. And so we're going to put a dot at 1 hour. At 0, I'm going to put a circle, not a dot. A circle there. Because if I go for no time, I have nothing there. At 0, I would pay $0. Right? So if I go for an hour and 1 minute, that's going to round me up to 2 full hours. And so anything over an hour up to 2 hours would be $170. Same thing when we go to 3 hours. Again, I'd have a circle at 2 hours, because again, if I go 2 full hours, I'm here. But if I go for 2 hours and a minute, I'm going to pay for the full 3 hours. So that's the function here. And so let's see what happens in the table. So here's my x's, here's my function, 85, greatest integer of x, and then what my y values would be. And so let's look at some values. A half, 1, 1.5, 2, and 2.5. And so what this function does is it will round up, because it's the greatest integer function, the value that is inside the brackets to the next integer. And so 0.5 would round up to 1. And so 85 times 1 is 85. And when I do it for 1 is an integer, so it stays where it's at. We're not going to round 1 up to 2. We're going to round to the next integer, but if we're already an integer, we stay where we're at. And so 1 times 85 is 85. When I do it with 1.5, well, 1.5 is not an integer, so I have to round up to the next integer. So that's 2. And so 2 times 85 is 170. And we continue that pattern here, and that's what we're going to see in the table. And so this will go to 170 because, again, 2 times 85. Then we do the 2.5 in here. 2.5 would round up to 3. 3 times 85 is 255. And so this pattern continues. Again, we can draw this all the way. And as much as you have a graph for it, you need to show as much as you can. Now again, if we have domain restrictions, so let's say we can max out at 4 hours, we would not show more than 4 hours on this graph. But again, whatever the graph gives you, do as much as you can, okay? And so we look at this example, the daily grind charges $1.25 per pound of meat or any fraction thereof. Draw a graph that represents the situation. And so this is, again, different than going to the grocery store and just buying meat, right? Because if you go and buy 1.5 pounds of meat, you do 1.5 times the $1.25 and get your total cost. But again, this is a step function, so it's going to be the 125 is our multiplier times the number of pounds. So we could use P, right? We could change our function notation to a P for pounds or L for pounds because that's the abbreviation LB. And we could even change our F to a C, right? So the cost based on the number of pounds. And so graphing this, we'll go to our graph here. Again, if I take 0 pounds, I pay nothing. But if I take anything of 1 pound, so again, if I take 1 ounce, I'm going to pay the full $1.25. Or if I get 16 ounces, 1 full pound, I'm going to pay $1.25. And this will continue up the chart again. Every $1.25, it is going to jump. And again, as you go up, make sure you get all of the graph as much as you can do. And so 10 is right here at the top. Okay. Now again, our domain, let's talk about domain and range for a second. Our domain, our p-values have to be greater than or equal to 0, right? Because it doesn't make sense to have negative pounds of meat. And our range would be that the cost is greater than or equal to 0. And again, if we're doing interval notation, 0 to infinity and 0 to infinity. Okay. Last examples, we talked about parent functions of absolute values yesterday in 2.6, just refreshing our memory of these pieces. And so when we look at this function, I'm just going to draw a little sketch here, 1, 1, 1, and 1. Look at these definitions. So the absolute value of x is such that these 3 pieces of a piecewise would happen. At 0, we're 0, right? When we're greater than 0, it's the function of x, which means I'm going to go up 1, right 1 from the origin and continue up this way. So it's this piece. And then negative x is when x is less than 0, so that's going to be a downward sloping function, a decreasing function, when we're before the y-axis. And so it is this piece going off to the left. And so the type of graph it is a V-shaped graph. It doesn't have a fancy name like a parabola or other type functions. The domain here is all real numbers from negative infinity to positive infinity because we see that these go on forever in x. But the range is that y is greater than or equal to 0 because there's nothing below the x-axis. So 0 to infinity, don't forget, is a bracket on the 0. Our x-intercept and y-intercept are the same. They are at the origin 0, 0. And this function is not defined when y, because remember that's f of x, when y is less than 0. And so just looking at a couple functions of absolute values here, our first one, y is equal to the absolute value of x plus 1. Go back to what we talked about yesterday. This plus 1 that's out back is going to shift this graph where? Where is it going to shift the graph? Remember, the plus 1 that's out back will shift it up. And so it's going to take all those y values of this function, this original function, right? That makes a nice little v. Okay? Again, makes our nice little v here. It's going to take all those dots and shift them up 1. So my vertex is now at 0, 1, and I head up in this direction and also in this direction. So again, my final graph is the red, not the blue. Domain and range. Domain, again, we said it's going to be all real numbers. Our range, we shift everything up. And so the bottom of this graph, the vertex, the minimum, is now at 0, 1. So y is greater than or equal to 1 instead of 0. So 1 to infinity. Okay. Last graph here. I know this video is going long. By the way, the word of the day is piecewise. Piecewise is the word of the day. And so our last graph here. This one's, again, an absolute value graph, but let's identify the pieces. First, we see that our vertex has been shifted up to 0, 1. And so that means I translated where? Up 1, right? So remember when we talked about our function yesterday, I would have that plus 1 out back from the parent. But the other thing that happens on this graph is that my slope has changed. In a normal absolute value function, my slope is 1 and -1 for the two pieces. But my slope here is now up to right 1. My slope is 2. And so if my slope has changed, it's going to change the multiplier out front. And so we're going to get y, or f of x, right? Because this is a absolute value function, f of x is equal to 2 times the absolute value of x, and then plus 1 out back. And the plus 1 is not inside the parentheses, or the absolute value bars. Remember, if it was inside the absolute value bars, this would be a shift either to the left or right, depending on the sign. In out back, it's vertical. Inside, it's horizontal. And so this is our function. Our domain here is still all real numbers. This isn't going to stop. Negative infinity to positive infinity. And our range, because we shifted this up, remember, our range will also shift up, and so y is greater than 1 or from 1 to infinity. And that's all I've got for you today. So again, we looked at 3 different types of graphs. We looked at piecewise functions. Again, you could have 2 or more pieces. We looked at absolute value functions, which was the last ones that we just looked at. And in the middle, we looked at step functions. And it looks like stair steps because they're just horizontal segments as we go up the coordinate plane. All right, you know what to do. If you got questions, ask. I hope this video has been great today, and we'll talk about it later.